Let's graph the rational function f of x is equal to 2x plus 6 over x minus 3 by finding all the intercepts and asymptotes. If you graph this thing into Desmos or your graphing calculator, you'll see that around x equals 3 there's a vertical asymptote, which I'll just abbreviate VA. This corresponds to where the denominator is equal to 0. So if you put a 3 in place of x, it'll create division by 0, and on the graph, you'll see at x equals 1, 2, 3, you'll see this vertical split, which I'll just represent with this dotted line. Another feature of the graph that you can see pretty easily by looking at the equation is the X-Intercept, which I'll just write X-Int. This appears wherever the numerator is equal to 0. So the numerator is 2x plus 6. If you put negative 3 in place of this x, the whole numerator is 0, and it makes the entire equation 0 as well. So the x-intercept is negative 3, 0. So just to recap, if you look at this equation, where the denominator is equal to 0 is a vertical asymptote, where the numerator is equal to 0 is an x-intercept. So I'm going to plot that x-intercept at negative 1, 2, and I'll put that here at negative 3. So we know a couple of things about the graph just by looking at the equation itself. Two other things to look for are the horizontal asymptote and the y-intercept. Now, the y-intercept occurs whenever x is equal to 0. So if you put 0 into all of the x's in this equation, the thing that is left over is the y-intercept. This is the ratio of the two numbers at the very end, which is 6 divided by negative 3. So that value is going to be negative 2. What this tells us is, at x is equal to 0, the y-intercept is at negative 1 down to negative 2. So let me graph that. The vertical asymptote comes from the ratio of the two numbers in front of the x's. So here I have a 2, there's really a 1 here, so 2 over 1 is going to be the horizontal asymptote, and that is a y value. So at 1, 2, I'll draw a horizontal line. The graph of the equation, 2x plus 6 over x minus 3, has to pass through the intercepts but also approach both asymptotes. So I know one part of the graph has to look like this, and the other one has to be up here. And we're looking for just a basic sketch of this graph. So here's what I'll do. Draw an equation going through those two intercepts and approaching the asymptotes. And I'll do the same thing over here. I'm not concerned with how big or small the y values are. I just want to make sure it goes through the intercepts and approaches the asymptotes. So just to recap, if you look at this equation, where the denominator is 0 is a vertical asymptote, where the numerator is 0 is an x-intercept, the ratio of the last two numbers was the y-intercept, and the ratio of the first two numbers was the horizontal asymptote. If we look at 2x plus 6 divided by x minus 3 in Desmos, this is the graph that I ended up with over here. So there's two things actually. There's this red graph. This is just the graph of 1 over x. And the blue graph refers to the function we just sketched in the previous example. Notice that at 3, there's this vertical split in the graph. At y is equal to 2, there's this horizontal asymptote. Here at negative 3, we have the x-intercept. And at negative 2, we have the y-intercept. So the picture in Desmos does in fact match up with the equation we just graphed. But what I'd like to do is just justify one of the ideas in the previous example, which is y is equal to 2, the horizontal asymptote. So why does that happen at y is equal to 2? If you go back to this original equation, this is a division problem. You're saying x minus 3 is being divided into 2x plus 6. If you do this division out, here's what we get. I would first want to cancel this 2x by multiplying x minus 3 by something. That number would have to be 2. When I multiply 2 to x minus 3, I get 2x minus 6. And then I have to subtract what I just put here. That's 2x minus 2x, which is 0. Then I have 6 minus a minus 6. That becomes addition, and I end up with 12. What this division problem just did for us is the following. It takes the equation 2x plus 6 over x minus 3, and it says, that's the same thing as dividing out 2, and you're adding this remainder of 12 out of x minus 3 left over. We saw that, well, the y value that's sitting here is the horizontal asymptote. And then you can look at this portion of the graph and say, oh, well, x equals 3 is the vertical asymptote. You can understand this entire equation by dividing it out and using transformations on the graph of 1 over x. The graph of 1 over x moves 3 places to the right, so it takes the vertical asymptote at x is equal to 0 and moves it over to x is equal to 3. This 12 stretches the graph because you're multiplying the y values by 12, so this thing is definitely stretched out. And then the whole equation goes up 2 places. Since the horizontal asymptote on 1 over x is y equals 0, it goes up 2 places to y is equal to 2. So just by using some division, you can see why the horizontal asymptote is the ratio of the two numbers in front of x. When I divide x minus 3 into 2x plus 6, it would have to be 2 that comes out. And if you wanted to try a different example, you could switch it. You could say, well, what if the graph was, 4x plus 6 over x minus 3? In this division problem, if you were to divide it out, you would definitely get 4 sitting here instead of 2, because you're trying to cancel a 4x instead of a 2x. But that is it for this, and we can check all of our graphs on a calculator or Desmos.